All right, today we are going to be looking at Chapter 5, gases, because we finished our last chapter. And gases have a lot of information. I'm going to open this all up here, and I'll go over it. All right. Gases take the shape of their container, and gases are the most compressible state of matter. There are 11 elements that exist as a gas at room temperature and normal atmospheric conditions. Normal atmospheric conditions just means what we live at. We live at 1 atmosphere of pressure, give or take a little bit. At sea level, it's supposed to be exactly 1 atmosphere. And I've listed a bunch of, not just a bunch of, all of the elements that exist as gases at room temperature and 1 atmosphere. All right, on to section 5.2. One of the things that's really important for you to understand about gases is how gas pressure is measured and what gas pressure is. So, gas pressure. Let's go to here. All right. Pressure is caused by gas particles hitting the walls of their container. So right now I'm hitting the wall in the classroom, and I'm pretending that my hand is a gas particle. And you may not feel it, but there are a whole bunch of gas particles hitting your skin, hitting your face, hitting you all over. If you went out into space, you'd be in what's called a vacuum where there are no gas particles, and there would be no molecules hitting your face or your eyes, or you wouldn't be able to breathe in. You'd have a vacuum in your lungs because all of the air in your lungs would get pulled out of you from the vacuum in space. So the pressure you're feeling, that you don't really feel like you feel it, but the pressure you're feeling is caused by a whole bunch of gas molecules hitting you all over the place. Now, as the number of collisions of these gas particles and or the force of the collisions of these gas particles increase, pressure goes up. So the more particles there are, the higher the pressure. The faster the particles hit you, the higher the pressure. And we're going to come up with an equation later that puts all of this right here into a mathematical formula. So we need to talk about units for pressure. 1 atmosphere is equal to 760 torr, which is the same as 760 millimeters of mercury, literally the height of the element mercury, how high the mercury will rise due to a gas inducing pressure on the mercury. That's equal to 101.3 kilopascals, which is equal to 14.7 pounds per square inch. You will not have to memorize all of these. You will be given these on tests and quizzes. Here are here are all the abbreviations that you'll need. Now, when you see ATM, I do not want you to read it as ATM. I want you to see this word ATM, or this abbreviation ATM, and I want you in your head to think atmosphere. If you see this abbreviation torr, you should think torr. If you see the abbreviation MMHD, you should think millimeters mercury. If you see kPa, you should think kilopascals. PSI, actually everybody says PSI. You should think pounds per square inch when you see that. All right, so how do we measure pressure? Pressure is measured with a specific device. One such device is a manometer, and we have 3 different manometers here. The first manometer is a closed manometer. You'll see this right here is closed. See how it's closed at the top? This one is open at the top, and the third one is also open at the top. Depending on the type of manometer, there's a different way or formula to calculate the pressure of the gas. The dark area in these manometers, this dark area, is the mercury. So here to here, this would be your mercury, and here to here would be your mercury. When we talk about millimeters of mercury, we're talking about the height that the mercury is pushed to from the gas or from the outside air. So in our closed, oh, sorry about that. I'm just trying to keep you on your toes here. In our closed manometer, the gas pressure is just the difference in height between how far the gas is pushing, and there's a vacuum. When you have this closed system, you have a vacuum in the top. So this height right here would be your gas pressure, because the gas is pushing down on the mercury, and the mercury is being pushed up, this much of a difference between the vacuum and the gas. All right. Now notice here, the gas is pushing down, and it's pushing the mercury lower on the left side than how high the mercury is on the right side. That tells us that the gas pressure is greater than air pressure. So pushing down on the right side is air, the pressure of air. So hopefully you can see the gas is pushing harder, and so the mercury is being pushed. Oops. Mercury is being pushed all the way up to here. And the difference in height between how hard the gas is pushing and how hard the air is pushing, that height difference, tells you how much more pressure the gas has compared to the air. So we would add the height difference if the gas is pushing harder. Now if we look at this next one all the way on the right side, we see that the air is actually pushing harder. This was an open manometer. So the air is pushing harder than the gas, because the air is pushing the mercury farther down, all the way down to here, and the gas is only pushing the mercury to this height right here. So the difference in these two heights, H3, would be subtracted from the air pressure to get the gas pressure. So when you're reading a manometer and trying to figure out what the pressure is, you have to be very careful in looking at whether the gas is pushing harder or the air is pushing harder. Okay, in this example on the right, the air is pushing harder. In this middle example, the gas is pushing harder. And you can see that because the gas is going lower than how high the air is pushing. So now we're going to do some problems just where we're converting pressure units. So we want to convert 26 millimeters of mercury to atmospheres. And we look at our conversion factors that we have. Let's see, where's our conversion? Here we go. So we want to convert from millimeters mercury to atmospheres. All of these different things are equal. So I don't have to go through torr over to atmospheres. I can convert directly from millimeters mercury to atmospheres. So I know 760 millimeters mercury equals 1 atmosphere. So I always start with my given, 26 millimeters mercury. I need to convert from millimeters of mercury to atmospheres. And that conversion factor that I was given is that 760 millimeters mercury is equal to 1 atmosphere. And we got to make sure our units cross out correctly. The millimeters mercury cancel. And we get 0.03421. What are my units? Atmospheres. Do I have the right number of sig figs? Of course not. Why would I be asking you that if I did? How many do I keep? I keep 2. Hopefully you got that. 0.034 atmospheres would be my final answer. I started with 2 sig figs, and I want to end with 2 sig figs right here. All right, next question. Convert 79.3 kilopascals to torr. Start with what you're given, 79.3 kilopascals. I'm going to write that as an abbreviation. And I need to convert kilopascals to torr. Notice I read kPa as kilopascals. And I look over on the other page to find out what my conversion factors are. And I see that I have 101.3 kilopascals. And I was trying to convert to torr, so that would equal 760 torr. I don't have to go through the millimeters of mercury. I can go direct from any pressure unit to any other pressure unit. So let's put in our numbers. It was 760 torr is 101.3 kilopascals. And we get 594.94 torr. Let's make sure our units canceled correctly. Kilopascal, kilopascal, we're good. Now I check my sig figs. I should keep 3. So we would have 595 torr. Hopefully you got that. Okay. That's it. Section 5.2 is over. Now section 5.3, we're going to race through it and we're going to use it for the rest of for section 5.5. I meant to say through section 5.4, not 5.5. Okay, so there are 3 gas laws that you should know. Sometimes these come up on SAT 2 tests. I don't make a big deal out of them because I don't think that memorizing things is important. I think that understanding things is important. So there's a famous chemist, physicist, researcher, Robert Boyle. Boyle's law says that pressure is inversely proportional. That funny looking symbol, if you've never seen it before, this symbol right here means proportional to. So pressure is proportional to 1 over volume. This is called an inverse relationship. You might remember this from algebra. If something is proportional to the inverse of another variable, that's called an inverse relationship. Okay, the next law, and mathematically, that gives us this equation right here. P1V1 is equal to P2V2. If we start at one set of conditions and we change something, we can use this equation right here to find a new pressure or a new volume, given an initial pressure and volume. Next law, Charles' law. Charles' law says that volume is proportional to temperature. Let's talk a little bit about why that is. As we increase temperature, what happens is that gas particles will start moving faster. So the velocity of a gas particle, depends on the temperature of the particle. Particles start moving faster, they're going to hit the walls of their container harder, and they're going to push out the walls of their container, assuming that the container is expandable and pressure is constant. You don't have to completely understand that yet. We'll talk about that more. But the physical idea of this is as temperature goes up, particles will move faster, hit the walls of their container harder, and if pressure is constant, then the volume of the container will increase because those faster moving particles will cause the walls to expand. All right, so this equation right here is Charles' law. V1 over V2 is T1 over T2. Sometimes it's written differently. Is this direct or inverse? This would be a direct relationship. Volume and temperature are directly related to one another. Direct relationship. All right, and the last one we will talk about is Avogadro's law. It says that volume is proportional to N, direct relationship. As moles, N is moles, by the way. N is moles, that's important to know. As moles increase, the volume of a container will increase. If we put more gas particles into a balloon, what happens to the balloon? It expands. So as moles go up, volume goes up. And here's our equation. V1 over V2 equals N1 over N2. That is a direct relationship or direct variation. So inverse would be something like Boyle's law, where one variable is proportional to the inverse of the other variable. Direct, the variable is proportional to another variable. Okay, and that is it for 5.3. We're going to combine all those laws into the ideal gas equation. And the ideal gas equation is PV equals nRT. Pressure times volume equals moles times R, the universal gas constant, times temperature in Kelvin, and all of that is written down. Don't worry, it's coming. So if you notice this, pressure, volume, we learned from Boyle's law, indirect, and so they're both on the same side because they're inversely related, inverse relationship. Volume and moles, direct relationship on the opposite sides of the equal sign. And volume and temperature, that's also a direct relationship. So volume and temperature on opposite sides of the equal sign. Okay, so this is written out in words, what I just said. Pressure times volume equals moles times the universal gas constant times temperature. R is the universal gas constant. It has these funky units. These units confuse students. These units do not mean that you should take the pressure and multiply by the volume and divide by the moles and divide by the temperature in Kelvin. And you will see here, temperature is in Kelvin. We have an equation for Kelvin. Those units just go along for the ride with the actual constant, 0.0821. They're just coming along for the ride, and I'm going to need to remake this square. Okay, so just be very careful when you're using the universal gas constant. It's just a number with it happens to have 4 different units in its one unit. Just like if we talk about velocity as meters per second, there's 2 units in there. Your velocity would have meters and seconds in them. So let's do some problem solving. All right, so here's our first problem. What mass of nitrogen gas is in 2.5 liters at 52 kilopascals and 25 degrees Celsius? So you might ask yourself, is this Boyle's, Charles, ideal gas law? What are we looking at? First thing we want to do is write down all of the different pieces of information that are given to us. So we know we have 52 kilopascals, we have 25 degrees Celsius, 2.50 liters, and grams equals question mark. Let's assign the variables. So what do these things represent? Well, kilopascals, you have to get used to those pressure units. We're going to recognize, hopefully, this is a pressure. Degrees Celsius would be a temperature. Liters would be a volume. Grams, you need to recognize, grams we're going to get to from moles. So really what we're looking for is moles, and then from the moles we can get to the grams. So if I see PTV and a question mark, hopefully you'll recognize, oops, I didn't need to go back that way. And now I can't get to where I want to go. Oh, I was in the right place. Sorry, I'm wasting your time here. This is where we want to be. Hopefully you'll recognize that we've got PV equals nRT. Now, the pressure units are atmospheres, so I'm going to have to convert my pressure to atmospheres. I'm going to always convert pressure to atmospheres. If it's in any other unit, I'll get it to atmospheres so that I can use this value of R. And the temperature I'm going to have to convert to Kelvin. So let's go back to our problem. So pressure, we're going to convert that to atmospheres, 52 kilopascals. And you check your conversion factors. It's 101.3 kilopascals is equal to 1 atmosphere. Okay, so that is equal to 0.513 atmospheres. And notice I kept 3 sig figs. It looks like I should only keep 2. I'm going to keep 3 for now, and at the very end of the problem, I'll do my final rounding. My temperature I need to convert to Kelvin, so it's going to be 25 plus 273, 298 Kelvin. Volume is in liters, that's the unit I need it in. And so we're going to solve for moles. N, we have the equation, PV is nRT. We're solving for N, and I've told you I like to see you isolate the variable that you're looking for and then plug in all of your information. So we have N is PV over RT. I will plug everything in. Pressure, 0.513. Make sure you write out all your units as you solve these problems. The volume, 2.50 liters. R, it was in that last page. It's 0.0821, and it's got a bunch of units with it. Atmospheres, liters over moles, Kelvin. We have to make sure we end up with the right units at the end. And temperature is 298 Kelvin. I just solved for that right there. Okay. You solve that, and I get 0.0524. Now let's check our units. What units do we end up with? We were solving for moles, so hopefully we'll end up with moles. The atmospheres cancel. The liters cancel. And here the Kelvin, do you see that? That also cancels. And notice I've got my moles in the denominator of the denominator, which means it's actually in the numerator. So here we go. There's our moles. Now, am I done with the problem? No, the problem asked for mass. So I've got to convert my moles. Notice I've still got 3 sig figs here. I cannot keep them all. I'm going to convert those moles of nitrogen gas. Now, on any homework problems, I will tell you this for now. Nitrogen gas has the formula N2. You might think it's just N. There's something called Hofbrinkel. We'll go over that later. But Hofbrinkel, those are all the elements that are diatomic, 2 atoms in the element, in the pure element. So I've got to get my moles to grams, use molar mass again. So I just need the molar mass of N2. 1 mole of N2 is 28.02 grams of N2. And that's 1.47 grams of N2. Now remember, let's go back to sig figs. So temperature looked like it was 2 sig figs, but actually temperature ends up being 3 sig figs because of our addition-subtraction rules. But pressure is still only 2 sig figs. So I can only keep 2, 1.5 grams of N2, and I have completed that problem. Let's do another one. Okay, second problem. What is the temperature of 64 grams of oxygen and 250 milliliters at 1490 millimeters of mercury? So again, let's identify what do all these numbers represent. We've got 64 grams of O2. We've got 250 milliliters. And we've got 1490 millimeters of mercury. And we want to find temperature. What is the temperature? So I just went through, listed all the numbers I was given. Now I have to identify what are those variables we're dealing with. Well, grams, no, we're in the gas laws. We don't ever have grams in any of our equations in the gas laws, but what we do have is moles, so we're going to have to convert this to moles. Milliliters, this will be our volume. Hopefully you recognize milliliters would be a volume. Millimeters of mercury, what is that? Hopefully you're getting familiar with all of the units for pressure. That's a pressure unit. And we don't know what temperature is. Now we have to look at the gas constant to figure out what kind of units does everything need to be in. Well, volume, the gas constant is in liters. So I need my volume in liters. Hopefully you know that 250 milliliters is 0.250 liters. We just moved the decimal left 3 places. Pressure, we're going to have to convert to atmospheres. So we have 1490 millimeters of mercury, and the conversion factor is 760 millimeters of mercury to 1 atmosphere, and that is 1.96 atmospheres. And I had 3 sig figs, I kept 3 sig figs. The moles, we're going to have to convert the grams to moles. grams of N2. Oops, we have grams of O2, not N2. And O2 is 32 grams to 1 mole. So that's going to be 2.00 moles of O2. And I'm solving for temperature, so we have PV equals nRT. And we know it's not Boyle's law or Charles' law because I've got moles, volume, pressure, and temperature. Well, there's only one equation I've seen that has all of those in it. It's this one right here, the ideal gas law. We're going to isolate temperature. Temperature is PV over nR, which will be 1.96 atmospheres. Volume, let's see, my volume was 0.250 liters. R, 0.0, oops, I have N there, but I'm going to do R first. Actually, we'll just do N first. 2.00 moles of O2. And R is 0.0821 atmospheres, liters over moles, Kelvin. And that is 2.98. And I check my units. Hopefully, I'm going to end up with a temperature unit. That does not seem right. Wow. Hold on one second. Okay, that calculated out, it is okay. That's a little low. I'm not sure that oxygen is actually a gas at this temperature. I think it is not. So I made up a bad problem here, but we'll keep going with it. Okay, so let's see what cancels. The atmospheres cancel, the liters cancel, the moles cancel. Kelvin is in the denominator of the denominator, which makes it in the numerator. So we are at 2.98 Kelvin. Check our sig figs. It looks like there's 3 sig figs in all the numbers I had. So that would be my final answer. The problem with this problem that I made up is that at 3 Kelvin, I'm pretty sure oxygen is a solid. But for the purpose of this problem solving, it works assuming that oxygen was a gas. And these were the conditions. It would be at 2.98 Kelvin. All right. New problem, two-state problems. Two-state means, instead of using just PV equals nRT, it means we start at one set of conditions and we change to another. It means we will be using either Boyle's law, Charles' law, or Avogadro's law. Sorry. So again, we just look and see what we have. We've got 25 degrees Celsius. We have 2.5 liters. What is the new temperature if the volume is increased to 5 liters? So I'm just writing down what I have. So I notice this 25 degrees Celsius is a temperature, 2.5 liters is a volume. Oh, look at that. I've got a temperature, a volume, a temperature, and a volume. So that's interesting. I've got temperature twice, volume twice. Two-state problems. Your variables will be listed twice. Notice this says at constant pressure. That means I just ignore pressure. So I'm going to have to use an equation with temperature and volume, and I have to figure out what are my 1s and what are my 2s. Where am I starting, where am I ending? So the gas is at these conditions. What is the new temperature? So hopefully you recognize the new temperature would be the second set of conditions. So what is the new temperature? I'm solving for T2. If the volume is increased, we're increasing the volume to 5 liters right here. This would be our V2. We were told that the gas is at 25 degrees Celsius, so we're starting at 25 Celsius in 2.5 liters. So I've got my T1, V1, T2, V2. Now, if you ever get confused, just write you don't have to memorize Charles and Boyle's and all those laws. Just have PV equals nRT, and notice we've got V and T. So I've got V's and T's, and that's a direct relationship. It's actually easier if you put the variables with the 2's on top, and then we'll put the variables with the 1's on the bottom. And there's my equation. Whenever you have a direct relationship, you can just put one variable over the other. And if you look, oops, I wrote that incorrectly. Sorry about that. That should be a T1, not a V1. T1. If you look back at Charles' law, you'll see this is Charles' law. It's just upside down, and it might be flipped left and right. All right. Now, temperatures have to be in Kelvin, so I have to add 273. This will be 298 Kelvin. And I don't have to convert anything else. So I'm trying to isolate T2. So I will solve this equation for T2. T2 is V2 T1 over V1, which is V2 5 liters, T1 298 Kelvin, V1 2.5 liters, and I get 596 Kelvin. And do I have the right number of sig figs? Let's see. Well, this was only 2 sig figs. The T1 ended up at 3 sig figs because the temperature, when you do addition subtraction, it's the placeholder. But this volume is also only 2 sig figs. I can only keep 2 sig figs. I have to write this like this. It's the only way to write that number with 2 sig figs. Okay, let's do one last problem. All right, a gas is in 250 mils at 765 millimeters mercury. The pressure is increased to 152 kilopascals at constant temperature. What is the new volume? Let's list all our variables. We have 250 milliliters, 765 millimeters of mercury, 152 kilopascals. Oh, temperature is constant, so I'm going to ignore the temperature. What is the new volume? Okay, let's figure out what all of these variables are. Milliliters would be a volume. Good. Millimeters of mercury. Are you getting used to those pressure units yet? That is a pressure unit. Kilopascals, not kPa, kilopascals. That's a pressure unit. And then the volume is, what is the volume? Now notice, do you see that we've got V listed twice and P listed twice? Hence, we have a two-state problem. Okay. With the, oops, go away. With the ideal gas law, you just see everything only once. Two-state, it's easy. You see the variables twice. We need to figure out the initial and the final. So the gas is in this volume at that pressure, and then we increase the pressure. So hopefully you recognize we're starting out at 250 milliliters. That's V1. At 765 millimeters mercury, that's our P1. We increase the pressure, P2. What is the new volume? That would be V2. That's what we're solving for. So what is our equation? You might want to look back at Boyle's law. You could see the equation there, or we can, because you're not going to have all these equations memorized in your head and you don't want to. We'll just write down the ideal gas law, PV equals nRT. And notice the only variables we see are PV. Everything else is constant. So what that's telling us is that P2V2 over P1V1 is 1. That's what that's telling us. If we only have pressure and volume, then P2V2 over P1V1 equals 1, or the way Boyle's law is written, P2V2 is equal to P1V1. We have some problems here. Do you notice? One of the pressures is millimeters mercury, one's kilopascal. We don't need to convert those both to atmospheres, we just need them both to be in the same units. So I'm just going to convert my millimeters mercury to kilopascal. 760 millimeters of mercury, 101.3 kilopascals. That comes out to 102 kilopascals. It's kind of hard to see that. Okay. And we are trying to solve for V2, so I will isolate V2 over here. V2 will be P1V1 over P2. Now we just plug in. I don't have to convert my milliliters to liters this time because I'm not using the ideal gas equation. I don't have to worry about the universal gas constant. So P1, V1, V1 kilopascals, 102 kilopascals over P2, 152 kilopascals. And that comes out to 167.7. Let's check our units. Whoop. Units. The kilopascals cancel, so I have milliliters. And now sig figs. I've got 3, 3, 3. I want to keep 368 milliliters. Note, I did not ask for the volume in liters or milliliters. It is fine to leave the volume just in milliliters. All right, that's it.